we have now reached one of the most popular problems in algebra, the cardboard box problems. We're looking a little bit more with optimization and really just interpreting what can happen when we go through this. So the idea behind the cardboard box problem, super important. Make sure you play with it now. It's going to show up again in the next sections. So it's nice to understand the idea. So I've got a kind of a concrete example to show, and then I'll show you the more abstract one that we will deal with in this particular section. So idea, we always start off with the rectangle, and they always give us some sort of information about the length and the width. So in our example one, we noticed that the length is 42 inches and the width is 23 inches. Then what happens is we cut out a same size or equal size square from each corner of our rectangular piece, our cardboard. And then we have a new shape. And what we're trying to understand when we go through this is once you cut out those equal size squares, you have to kind of determine what the new length and what the new width would be. And we have to kind of use concepts from our past. So kind of keep in mind, if you're starting out with the length of 42 inches and you cut off 2 inches, I'll try to color code that for you. So we cut off 2 inches here and we cut off 2 inches here. We have leftover amount. So this new length that we're trying to come up with should be 42 minus 4 because you cut off 2 inches twice. Now, if we want to talk about 42 minus 4, what do we have? 42 minus 4 is 38 inches. So that new length, when we kind of, after we translate this over, we should have 38 inches. So that is the concept, knowing how much you're really cutting off. Same story with the width. You're starting out with 23 inches and you're cutting off 2 and another 2. So the new width should start off at 23, but you're actually cutting off 2. So minus 2 means minus 4. And 23 minus 4 will give us 19 inches. So we're always coming up with the new dimensions once we have cut off those squares and folded the sides up. The other interesting part is to understand you just went from a 2-dimensional figure now to a 3-dimensional figure, flat piece of cardboard now to box. You will have one more dimension besides length, width. You're going to have your height. And if you could picture this, or maybe you have to do this at home and actually bring out the scissors and do the folding up, it's really very powerful. Sometimes just seeing it live in action. But I would say when you're looking at it, the 2 edges that get folded up, they end up meeting, that's 2 inches high. So you actually have your height as well. And so you'll start to see the pattern of this. So once you understand what the length is, what the width is, and what the height of this new box is, you can automatically go into volume now. So volume, we have a formula, length times width times height. We can actually fill this in. So what do we have? Length is 38 inches. Width is 19 inches. And height is 2 inches. So if we're actually doing the multiplication, because we have concrete numbers, we'll pull out our TIs just to do the quick multiplication. 38 times 19 times 2 gives us 1,444. And also keep in mind units. When we're dealing with volume, we have inches times inches times inches, or what we call cubic inches. So sometimes, I guess in the real world, you would refer to it as cubic inches, but we do have math speak for this as well with the exponent and the abbreviation. So if you could kind of train yourself to think back to this problem when you do end up seeing the next problem, this will kind of help greatly in setting up the volume, because that's kind of the most of the battle there. So are you ready? I thought so. We're going to move on. Okay, so same idea. What we want to do is start off with a rectangular piece of cardboard, understand what we're cutting out, and try to come up with the new lengths and widths. So let's read this first off. The length of a piece of cardboard is 8 times its width. So right away, they didn't straightforward give us the numbers, but they gave us a relationship. So they gave us that length, and I'll use L, is 8 times, so 8 times the width, 8 times W. Now, before I commit to using L and W, I have to be careful if anything else in the problem is telling me not to use L and W. So we'll go through this. To make a box with an open lid, a 3-centimeter square was cut from each corner. Well, we can draw that here. We know that we're cutting off the 3 centimeters from everywhere. If you need to, sometimes I label it all the way around. It does help me, but I'm cutting it off from everywhere. Okay. Let X represent the width of the cardboard. Okay, so we kind of almost there. Instead of using W, we shall use X. Maybe it's just more popular because we get to use it with our TI. Okay, so now I can start dealing with my dimensions. If I'm thinking about what the width was of the original cardboard, that would be X. And my length should probably be 8X. So even though these are not concrete numbers, we can still work with them. So now the next goal is to figure out what happens when we cut out the 3-centimeter square from each side. So you got to think about how much are you really subtracting off your entire rectangle. You would be cutting out 3 centimeters from one side and also 3 centimeters from the other side. So you're really saying 8X minus 3 minus another 3 should give us 8X minus 6. So that, my friends, should be the new length of your box. Now, similarly, if we want to do this with the width, we keep in mind for ourselves, we'll start off with X, and we're going to cut off 3 from one side and 3 from the other side. So that is also X minus 6. So starting off with original width and cutting off the 3 centimeters on each side. So now we've got our width labeled as X minus 6. And then understanding what happens when you fold the corners up, keeping in mind when we do fold the corners up on the box, the actual length of the square or a side of the square ends up actually being the height. So that, my friends, is 3 centimeters. So we actually have the length, the width, and the height, which is very important to kind of determining the rest of this problem. So at this point, you might be really excited and you can jump on to volume. But right now, they didn't quite mention volume at the moment. I do want to point out there's an issue. When we don't know the exact values of our length and width, we can't just choose any length and width. There's something that we call a feasible domain, otherwise known as restrictions. If you cut off too much from the length or width, you might end up with no box at all. So this is what we have to really figure out before we proceed forward with calculating anything else. So when we're asked what is the restriction on X, we just kind of keep in mind everything we know about real life dimensions. All these dimensions always have to be positive in order for us to have an object to begin with. So when the length, width, and height must be positive, sometimes I'll just kind of note to myself, length must be positive. And so what does that mean? Positive. If I'm really looking at this, positive means a number greater than 0. So the length must be positive, the width must be positive, and also the height. Otherwise, we do not have a box to begin with. So I kind of always begin by translating the English to a little bit of math. And then I'll try to kind of go back and say, well, do I have an expression for length? Do I have an expression for width? And do I have something for height? And we took the time to do this, so we actually do. So the length is 8x minus 6 greater than 0, according to what we're trying to figure out with restrictions. Width is x minus 6. And now the height, it's already a number. It's just 3. It is greater than 0. So that part is already done. We're good here. Check. So after we set these situations up, or what we call the feasible domain, what you end up dealing with, you have a link word now. We have ourselves a compound inequality. And you're thinking, an inequality of what? Well, we have a linear inequality and another linear inequality. So these are linear inequalities. We can resort back to methods from chapter 1 to help us solve these. Linear inequalities, we don't have to use the sign analysis method. All we do is isolate the values of x, so we can solve them. So that's the first thing I do. I'll isolate x for these linear inequalities. So that's going to leave me with 8x. If I add 6 to both sides, it's going to be 8x is greater than 6. Divide both sides by 8. So I should have x is greater than, because we're dealing with dimensions, we don't really have to have proper fractions or anything like that. 6 over 8 is a 0.75. Sometimes it's easier to really picture these. Now the other linear inequality I want to deal with, I need to deal with x is greater than 6. Again, I'm isolating the x. I did a little mental math, but really you're adding 6 to both sides. And if we do that, what happens? X does become greater than 6. So when you solve this compound inequality, you have to think about the link word. We have and. And a lot of times how I like to look at these, I know maybe you might be able to work mentally. But what I always prefer is just draw a quick picture, and then you can really see, you know, is there an inequality that covers both of these at the same time? So quick little number line. Got to solve the compound inequality. And when we do that, I do a quick picture. I plot 0.75 in relation to 6. And then I'm just trying to understand, well, if I'm talking about x is greater than 0.75, it would be shading to the right. And I would have a parenthesis opening up to where I shade. If I talk about x is greater than 6, I would be shading to the right of 6. And I would have a parenthesis opening up to where I shade. So now if we're dealing with link word, and we are looking for the intersection. And the intersection is where we have colored twice. And right away you can see right here. So the actual restriction on x is actually just the inequality x is greater than 6. Because I guess, you know, if you're greater than 6, aren't you also greater than 0.75? So this is what we would be answering for this part. So that's a little procedure in itself. It takes a little longer, but really just think about what happens if you were to have a length or width of 5 or something smaller than 6. What happens when you start subtracting off? If you have 5 minus 6, what happens is you get a negative dimension, and that won't make a box at all. That's impossible to us. So it's really, really important to really start off with understanding what the restriction would be before you start buying the materials and creating the box, because then you have a bunch of waste happening. If you cut the rectangles too big, you don't end up having boxes. You've just spent a lot of money and your company gets angry at you. So you want to hire a mathematician to figure this part out first, or, you know, at this point, because you're taking this class, now you can figure it out on your own. So once you're done with the restriction, which by the way will help us in a second or so, now we're going to go and say, well, what do we know about the volume of the box? Remembering for ourselves, volume is a length times width times height. We're going to go back and figure out what were our dimensions again. I believe we had 8x minus 6 as the length, x minus 6 as the width, and I believe it was a 3. Yes, it was. 3 centimeters as the height. So if you'd like to record this, length times the width times height. Now your TI will record this just fine. You don't really have to worry about the order. But sometimes when you check your answer in the back of the book, or you start writing stuff down, people often use the commutative property of multiplication. They always like to put the monomial before everyone else. So if you'd like to, that's fine too. It just kind of makes it a little prettier on the eyes, but really that's not necessary. So just kind of double check. Your calculator will handle either version. So we got part B down, length times width times height. And really the goal was, the hardest part of everything is always coming up with the dimensions. So it does take a little time to go through this. So now that we got an expression for volume, they're going to ask us a question about volume. And they want to know, for what values of x will the volume be between 300 cubic centimeters and 700 cubic centimeters? So what you're kind of asking yourself, if you want to look at this a little bit clearer, the volume has to be between two numbers. Those numbers have to be 700 cubic centimeters and 300 cubic centimeters. Now, if you already have an expression for volume, which we do, what do we have? 3 times 8x minus 6 times x minus 6, less than 700, greater than 300. What you now have is a 3-part inequality. However, this is not really a nice 3-part inequality, because if you were, which you don't have to, and I wouldn't recommend trying to multiply anything out, this would be a quadratic expression. Can you guys see why? Pause for a second. Well, if you were to multiply 8x times x, you're going to have yourself an x squared term. So that's going to kind of throw a little bit of a wrench into our process, because it's really hard to solve quadratic inequalities that have 3 parts to it. We could play around with sign analysis and go through this, but this would be a great opportunity to pull our TIs out, to really go through this. And this is kind of the benefit of having this technology. We could kind of switch off to what works best for us. So if we were to do this, I will pull out my TI. And what I'd like to do for myself is kind of keep in mind with the TI, usually what happens is we'll probably put our Y1 as our volume expression. And then our Y2s, I'll say the 300. And then my Y3, I'll make it the 700. So I'm looking for all 3 kind of numbers when I relate my TI. So I'll pull that over for you so you can see. Let's do that. So we have work from our previous part. But let's look at y equals one more time. And I'll put the volume in there. So 3 times 8x minus 6 times x minus 6. And notice you never have to multiply it out. The calculator will deal with it in this form. Now we're looking in between 300 cubic centimeters and 700 cubic centimeters. Now you could press graph now, but I would like to kind of give you a heads up. When you say y equals 300 and y equals 700, your window, if it's in standard viewing form, you're not going to see the entirety of all the three functions that you graphed. So what I kind of prefer to do is if I already know y could equal 300 cubic centimeters or y could equal 700 cubic centimeters, I may go to my y max just a little bit. Right now it's only at 10. I definitely pick a number above 700. So just to be kind of clear, maybe I'll just do 1,000. You could try 800 if you'd like. If you only pick 700, you may not see the entire screen. So I want to make sure I have that. So let's try to graph and see what we see. Okay, so now we see all three functions. And if you kind of really interpret what's happening, the blue curve is your volume, and red line is 300 cubic centimeters, black line, horizontal line is 700 cubic centimeters. You care about the x values for which your volume is in between these two lines. But then again, you notice, wait a second, my volume is in between these two lines at two places. You know, which place should I care about? And you kind of think about it a little harder and you say, wait a second, if I look at this part on the left of the y-axis, this would be implying that my x values are negative. So that would not be in our feasible domain. Hence, why we took the time to figure out a restriction. And what the restriction does for us, we don't even have to look at this entire graph anymore. The restriction being x is greater than 6, you can go to your window right away. And instead of having an x min of -10, if your x has to be greater than 6, make the x min 6 and graph it again. And you will see the region of the graph you really care about. So you don't have to have a comprehensive graph and see the entire volume. You just have to understand the context of your situation. And this, again, is why mathematicians make the big bucks, because they can relate this real life situation with their mathematics. So kind of keep that in mind, a little motivation for you. So what I'll do for myself, I'll probably sketch this on a piece of paper. So I'm going to go back just so that you kind of see. If I were to show work, just so I know how I solved it, what I'm really looking at is I have my volume, and I have my y2 equals 300, and my y3 equals 700. And in some case, if I go back and double check for myself, I kind of had like a square in a sense. There was really nothing to do with the axes except for the y-axis. So let's go back just so that you can see. So I'll just kind of look at it like so. Well, like so. There we go. Okay, so just in case you're wondering about the labels, I have y3, I have y2, and I have my volume, y1. So now what I'm really concerned about, again, what are they asking? For what values of x will the volume be between? So right now what we care about is a region. What's happening when the volume is in between y2 and y3? And also we care about what are these x values that make the volume in between y2 and y3, or 300 cubic centimeters and 700 cubic centimeters. So guess what? You guys have to find those x values, and if you have your TI, what technique would we be using? If you were thinking intersection method, you are correct. So we basically have to pull our TI with the command function so we can find those X values. So let's go do that. All right, so our favorite button, one more time, second trace. And we're going to find the intersection. That's item number 5. And you notice right now the cursor is located by the intersection at the bottom. So that can be our first curve. We press enter and it goes automatically to the second curve of which we want to find the intersection. So this is good. We'll press enter one more time and make it guess. And right now we have X is 7.7785. I take 4 decimal places. So I want to write that down and I come back to this TI. So let's go back. And that first X value, now that I know, I have about 7.7785 centimeters. So I'm good there. And I really want to find that second value. So we're going to go back to the TI. And we're going to calculate a second intersection. So if we do that, second calculate intersection, it is still stuck at the first intersection. So what I prefer to do is move along the curve. You're going to see me move the cursor using the left or right arrow. I'm going to move closer to the intersection that I care about. And I know I'm still on the first curve. I just wanted to make sure I'm clear. Sometimes it keeps calculating the first intersection all over again, but you already know that. So we do have the first curve. And then notice what happens. It doesn't automatically jump to the intersection that you care about. It's still stuck on the second curve. So when you have more than one curve graphed on your TI, how do you get up there? Well, glad you're watching because I'm going to tell you. You press the up and down arrows to toggle between the functions. So let me show you. I can press up and notice right now the cursor is now located on Y1, i.e. the volume. If you press up one more time, you will notice that the cursor moved to the next curve. And you can keep pressing up or down and it toggles between all of the curves so that you know how to move just in case. Left and right will only move you along the curves, but it won't switch between the curves. So that's a very important part that we learn as we're playing with our TI. So we want the intersection of the volume and 700 cubic centimeters. It looks like the 2 cursors are where we want them to be. We're going to press enter and make it guess. And right now we also have 9.37. So it's 3797. So 3798 if we're rounding with 4 decimal places. So let's go back and record our findings. So I should be looking at 9.3798. And now if you're kind of thinking, okay, we found those particular X values, what did the problem want? It wanted all of the values of X for which the volume is going to be in between 300 cubic centimeters and 700 cubic centimeters. So if you only list the 2 X values that you found, that's not entirely the correct answer. You actually want to list the region between these 2 numbers. So your solution for this particular question, you would have to give us 7.7785 centimeters is less than X is less than 9.3798 centimeters. So that's giving you the region. Or if you prefer interval notation, then it would be 7.7785 to 9.3798. So make sure you have either of the 2. If you only list the 2 numbers, you're giving the boundary points. You're not giving those particular values. You're only giving the values for which the volume is equal to Y2 or equal to Y3. So hope this helps. If I were you, I always try this example one more time, erase your notes or look at a blank piece of paper, see if you can do this and work through the steps on your own. And the more you do this, the more you practice, the more it's like second nature. So still, very important problem in college algebra. Make sure you know how to do this. And if you don't know how to do this, it's okay. You still have a chance again to redeem yourself. We're going to hit this up again in 3.7. So might as well learn it now. Hope this helps. See you next section.